Have you ever wondered what's happening at the very core of reality? From the tiniest particles to the vast expanse of the universe, the quantum world holds secrets that will leave you questioning everything you thought you knew. Imagine a world where particles can exist in multiple places simultaneously, where observing something fundamentally changes its behavior, and where two particles separated by vast distances can instantaneously affect each other. This isn't science fiction. This is the quantum world, a realm that exists all around us and within us, governing the behavior of everything from the smallest atoms to the largest structures in the universe. Welcome to an exploration of quantum mechanics, one of the most revolutionary and mind-bending theories in the history of science. Today, we'll journey from the microscopic realm of atoms and subatomic particles to the cosmic scale of galaxies, discovering how quantum principles shape our reality in ways that challenge our most basic intuitions about how the world works. Quantum mechanics is a branch of physics that describes the behavior of matter and energy at the atomic and subatomic scale. Unlike the predictable, deterministic world of classical physics that governs our everyday experience, quantum mechanics reveals a universe that is fundamentally probabilistic, uncertain, and often paradoxical. The word quantum comes from the Latin word meaning amount or portion. It refers to the discovery that energy, matter, and many other physical properties exist in discrete, indivisible units or quanta. Just as you can't have half a coin or a fraction of an electron, many properties in the quantum world come in specific, unchangeable packages. The birth of quantum mechanics began in 1900, when German physicist Max Planck proposed that electromagnetic energy could only be emitted or absorbed in discrete packets, which he called quanta. This revolutionary idea emerged from his attempts to solve the black body radiation problem, a puzzle that classical physics couldn't explain. Planck's work laid the foundation for what would become one of the most successful theories in physics. Albert Einstein further developed quantum theory in 1905, when he explained the photoelectric effect, demonstrating that light itself consists of particles called photons. This work, for which he won the Nobel Prize, showed that light has both wave-like and particle-like properties, a concept known as wave-particle duality that would become central to quantum mechanics. The theory was further developed by brilliant minds like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and many others throughout the early 20s. Together they created a mathematical framework that could accurately predict the behavior of atoms and subatomic particles, even though this behavior defied common sense and everyday experience. Quantum mechanics challenges our understanding of physical reality in profound ways. The quantum world operates according to principles that seem to violate our basic intuitions about how things should behave. Let's explore three of the most mind-bending quantum phenomena that have revolutionized our understanding of reality. Perhaps the most famous concept in quantum mechanics is superposition, the idea that quantum particles can exist in multiple states simultaneously until they are observed or measured. Unlike classical objects that have definite properties at all times, quantum particles exist in a superposition of all possible states. The most famous illustration of this concept is Schrödinger's cat, a thought experiment proposed by Austrian physicist Erwin Schrödinger. In this hypothetical scenario, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a flask of poison. If the atom decays, a quantum event with a 50% probability, the Geiger counter detects it, triggers the hammer to break the flask, and the cat dies. According to quantum mechanics, until someone opens the box and observes the system, the atom exists in a superposition of both decayed and not decayed states, making the cat simultaneously alive and dead. While this seems absurd for macroscopic objects like cats, superposition is very real for quantum particles. Electrons, for example, can spin in multiple directions simultaneously, and photons can travel through multiple paths at the same time. This bizarre behavior has been confirmed through countless experiments and forms the basis for emerging technologies like quantum computers. Quantum entanglement is perhaps even more mysterious than superposition. When two or more particles become entangled, they form a single quantum system, where the quantum state of each particle cannot be described independently. Measuring one particle instantly determines the state of its entangled partner, regardless of the distance separating them. Einstein famously called this phenomenon spooky action at a distance, because he was deeply uncomfortable with the idea that particles could influence each other instantaneously across vast distances, seemingly violating the principle that nothing can travel faster than light. Along with colleagues Boris Podolsky and Nathan Rosen, Einstein proposed what became known as the EPR paradox in 1935, arguing that quantum mechanics must be incomplete. However, decades of experiments have consistently confirmed that entanglement is real. In 1964, physicist John Bell developed a theorem that provided a way to test whether the correlations predicted by quantum mechanics could be explained by local hidden variables, as Einstein preferred. Subsequent experiments, particularly those conducted by Alain Aspect in the 1980s and many others since, have definitively shown that quantum entanglement is genuine, and that Einstein's local realism cannot explain quantum phenomena. The implications of entanglement extend far beyond academic curiosity. Scientists are now harnessing entangled particles for quantum communication, quantum cryptography, and quantum computing. The phenomenon suggests that at the quantum level, the universe is deeply interconnected in ways that classical physics never imagined. Quantum tunneling is another phenomenon that defies classical intuition. In the classical world, if you roll a ball toward a hill, the ball needs enough energy to go over the hill to reach the other side. If it doesn't have enough energy, it will roll back. In the quantum world, however, particles can tunnel through energy barriers even when they don't have enough energy to go over them. This happens because quantum particles are described by wave functions that give the probability of finding the particle at any given location. Even when a particle encounters a barrier it classically shouldn't be able to cross, there's a small but non-zero probability that the particle's wave function extends beyond the barrier. This means the particle can spontaneously appear on the other side, having effectively tunneled through the obstacle. Quantum tunneling might seem like a purely theoretical curiosity, but it plays crucial roles in many natural processes and technological applications. Nuclear fusion in the Sun relies on quantum tunneling. Protons in the Sun's core don't have enough energy to overcome their mutual electrical repulsion classically, but quantum tunneling allows them to get close enough to fuse, powering our star and making life on Earth possible. In technology, tunneling is essential for the operation of many modern devices. Tunnel diodes, scanning tunneling microscopes, and flash memory all depend on quantum tunneling effects. Without this quantum phenomenon, much of our modern electronics wouldn't function properly. Quantum mechanics in modern technology. While quantum mechanics might seem abstract and removed from everyday life, it forms the foundation of numerous technologies that we use daily. The quantum revolution of the 20th century didn't just change our understanding of physics, it transformed our world through practical applications that have become integral to modern society. Lasers represent one of the most visible applications of quantum mechanics in everyday life. The word laser stands for light amplification by stimulated emission of radiation, and the underlying principle relies entirely on quantum mechanical processes. In a laser, atoms are excited to higher energy levels, creating what's called a population inversion. When these excited atoms are stimulated by photons of the right frequency, they emit additional photons that are identical in frequency, phase, and direction to the stimulating photon. This process, called stimulated emission, was first theorized by Einstein in 1917 and is purely quantum mechanical in nature. The result is a highly focused, coherent beam of light with applications ranging from barcode scanners and DVD players to surgical procedures and fiber optic communication. Lasers are used in manufacturing for cutting and welding materials with extraordinary precision, in research for spectroscopy and interferometry, and in medicine for everything from eye surgery to cancer treatment. The development of lasers has also enabled entire industry. Without lasers, we wouldn't have compact discs, fiber optic internet, laser printers, or the precise manufacturing processes that make modern electronics possible. The global laser market is now worth tens of billions of dollars annually, all built on quantum mechanical principles discovered over a century ago. Perhaps even more fundamental to our modern world are transistors, the basic building blocks of all digital electronics. Every computer, smartphone, and digital device contains millions or billions of transistors, all of which operate based on quantum mechanical principles. Transistors are made from semiconductor materials, like silicon, whose electrical properties can be precisely controlled through a process called doping, adding small amounts of other elements to alter the material's quantum mechanical band structure. The behavior of electrons in these materials is governed entirely by quantum mechanics, particularly the wave nature of electrons and the quantum mechanical concept of energy bands. In a transistor, the flow of electrical current is controlled by applying voltage to a gate electron. This voltage changes the quantum mechanical energy levels in the semiconductor, either allowing or preventing electrons from flowing through the device. The ability to switch current on and off rapidly and reliably makes transistors perfect for representing the binary digits, bits that form the basis of digital information. The exponential growth in computing power over the past several decades, often summarized by Moore's law, has been driven by making transistors smaller and smaller. Modern processors contain transistors with features just a few nanometers wide, so small that quantum effects become increasingly important and sometimes problematic. As we approach the fundamental limits of transistor miniaturization, the technology industry is exploring new quantum mechanical phenomena to continue advancing computing power. Magnetic resonance imaging, MRI, represents one of the most sophisticated applications of quantum mechanics in medicine. This technology, which allows doctors to see detailed images of soft tissues inside the human body without using harmful radiation, relies on the quantum mechanical property of atomic nuclei, called spin. In quantum mechanics, many particles have an intrinsic angular momentum called spin, which creates a magnetic moment. In MRI, the focus is on hydrogen nuclei, protons in water molecules, throughout the body. When placed in a strong magnetic field, these protons align their spins, either parallel or anti-parallel to the field, with slightly more aligned parallel to the field, due to the lower energy. Radio frequency pulses are then used to flip the spins of these protons, temporarily disturbing their alignment with the magnetic field. When the radio frequency is turned off, the protons relax back to their original alignment, emitting radio signals in the process. The frequency and intensity of these signals depend on the local chemical environment of the protons, allowing doctors to distinguish between different types of tissue. The quantum mechanical nature of this process is essential. Classical physics cannot explain the discrete energy levels of nuclear spins, or the precise frequencies at which they absorb and emit electrons. The mathematics of quantum mechanics provides the framework for understanding and predicting these interactions, enabling the sophisticated image reconstruction algorithms that produce the detailed anatomical images we see in medical diagnostics. MRI technology has revolutionized medical diagnosis, allowing doctors to detect tumors, brain abnormalities, joint problems, and many other conditions without invasive procedure. The development of MRI earned Paul Lauterbur and Peter Mansfield the 2003 Nobel Prize in Physiology or Medicine, recognizing the profound impact this quantum-based technology has had on human health. While quantum mechanics is often associated with the microscopic world, its influence extends far beyond atoms and subatomic particles. The quantum nature of matter and energy shapes the behavior of objects at every scale, from the smallest particles to the largest structures in the universe. Chemical bonding, the force that holds atoms together to form molecules, is entirely quantum mechanical in nature. The electrons that orbit atomic nuclei don't follow classical planetary orbits, but instead exist in quantum mechanical orbitals, three-dimensional probability distributions that describe where electrons are likely to be found. When atoms come together to form chemical bonds, their electron orbitals overlap and interact according to quantum mechanical rules. The strength, geometry, and properties of these bonds determine the structure and behavior of molecules, from simple water molecules to complex proteins and DNA. Without quantum mechanics, we couldn't understand why carbon forms four bonds, why water is bent rather than linear, or why some molecules are stable, while others are highly reactive. In biology, quantum effects play crucial roles in many life processes. Photosynthesis, the process by which plants convert sunlight into chemical energy, relies on quantum mechanical energy transfer. When chlorophyll molecules absorb photons, electrons are excited to higher quantum energy levels, initiating a cascade of quantum mechanical processes that ultimately store solar energy in chemical bonds. Recent research has revealed quantum effects in other biological processes as well. Some birds appear to use quantum entanglement in their navigation systems, detecting Earth's magnetic field through quantum processes in their eyes. Enzymes, the biological catalysts that make life's chemistry possible, may use quantum tunneling to speed up chemical reaction. Even the sense of smell might involve quantum mechanical recognition of molecular vibrations. The very existence of elements heavier than hydrogen and helium depends on quantum mechanical processes occurring in the cores of stars. Nuclear fusion, the process that powers stars and creates heavier elements, is only possible because of quantum tunneling. In stellar cores, temperatures reach millions of degrees, but even at these extreme temperatures, atomic nuclei don't have enough kinetic energy to overcome their mutual electrical repulsion through classical physics alone. The quantum mechanical phenomenon of tunneling allows nuclei to approach each other closely enough for the strong nuclear force to bind them together, despite not having sufficient classical energy to overcome the electrostatic barrier. This quantum-enabled fusion process is responsible for creating most of the elements in the periodic table. Hydrogen fuses to form helium, helium fuses to form carbon and oxygen, and so forth, building up heavier and heavier elements through successive generations of stars. When massive stars reach the end of their lives and explode as supernovae, these quantum-forged elements are scattered throughout space, eventually becoming incorporated into new stars, planets, and ultimately, living organisms. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all created through quantum mechanical processes in stellar cores billions of years ago. In a very real sense, we are made of quantum stardust, connected to the cosmos through the fundamental laws of quantum physics. On the largest scales, quantum mechanics may have played a crucial role in shaping the structure of the universe itself. According to current cosmological theories, the tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang, originated from quantum mechanical uncertainties in the very early universe. During a period called cosmic inflation, quantum fluctuations in the energy density of space were stretched to cosmic scales, providing the seeds around which galaxies and galaxy clusters would eventually form. These quantum uncertainties, governed by Heisenberg's uncertainty principle, were amplified by the rapid expansion of space during inflation to create the large-scale structure we observe in the universe today. The cosmic microwave background, observed by satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft, shows tiny temperature variations that correspond exactly to what we would expect from quantum fluctuations in the early universe. These observations provide compelling evidence that quantum mechanics operates not just in laboratory settings, but on the grandest scales imaginable. As our understanding of quantum mechanics deepens, and our ability to manipulate quantum systems improves, we stand on the brink of a second quantum revolution. Emerging technologies promise to harness quantum effects in unprecedented ways, potentially transforming fields from computing and communication to sensing and simulation. Quantum computers represent perhaps the most exciting frontier in quantum technology. Unlike classical computers that process information using bits that can be either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in superposition states of both 0. This quantum parallelism allows quantum computers to explore multiple computational paths, simultaneously potentially solving certain types of problems exponentially faster than classical computing. While still in their early stages, quantum computers have already demonstrated quantum supremacy for specific tasks, performing calculations that would be impossible for even the most powerful classical supercomputer. Applications for quantum computing include cryptography, drug discovery, financial modeling, artificial intelligence, and simulation of quantum systems. As quantum computers become more powerful and reliable, they may revolutionize industries and enable discoveries that are currently beyond our reach. Quantum mechanics also promises to transform how we communicate and secure information. Quantum key distribution uses the principles of quantum mechanics to create unbreakable codes. Any attempt to intercept a quantum encoded message necessarily disturbs the quantum states involved, alerting the communicating parties to the presence of an eavesdrop. Quantum networks, which use entangled particles to transmit information, are being developed to create ultra-secure communication channels. These networks could protect everything from financial transactions to government communications, providing security guaranteed by the laws of physics rather than mathematical complexity. Quantum sensing and metrology. Quantum mechanical systems are exquisitely sensitive to their environment, making them ideal for precision measurements. Quantum sensors can detect tiny changes in magnetic fields, gravitational fields, time, and other physical quantities with unprecedented accuracy. Applications for quantum sensing include navigation systems that don't rely on GPS, medical imaging with improved resolution, searches for dark matter and gravitational waves, and geological surveys for oil and mineral exploration. As these technologies mature, they may enable discoveries about the fundamental nature of space, time, and matter. The discoveries of quantum mechanics have profound implications that extend far beyond technology and science. They challenge our most basic assumptions about the nature of reality, causality, and the role of observation in the physical world. The measurement problem in quantum mechanics raises fundamental questions about the nature of physical reality. Does the wave function collapse represent a real physical process, or is it merely a limitation of our knowledge? Different interpretations of quantum mechanics, from the Copenhagen interpretation to many worlds theory, offer different answers to these questions, each with profound implications for our understanding of reality. The role of consciousness in quantum mechanics remains a subject of debate. Some interpretations suggest that conscious observation plays a special role in determining physical outcomes, while others maintain that any interaction with the environment, conscious or not, can cause wave function collapse. These questions touch on deep philosophical issues about the relationship between mind and matter. Quantum mechanics also raises questions about determinism and free will. If the future is genuinely uncertain at the quantum level, does this provide room for free will in a way that classical determinism does not? Or does quantum randomness simply replace classical predictability without fundamentally changing our understanding of causation and choice? The quantum world is not separate from our everyday experience. It is the foundation upon which our everyday experience rests. Every atom in our bodies, every photon of light we see, every chemical reaction that sustains life, operates according to quantum mechanical principles. The technologies we depend on, from computers to medical imaging, from GPS navigation to solar panels, all rely on our understanding and manipulation of quantum effects. As we continue to explore the quantum realm, we uncover new mysteries and possibilities. Quantum mechanics has taught us that the universe is far stranger and more wonderful than our ancestors ever imagined. Reality is not the solid, predictable clockwork that classical physics once suggested, but a dynamic, interconnected web of possibilities and probability. The journey from atoms to galaxies reveals the profound unity underlying the apparent diversity of the physical world. The same quantum principles that govern the behavior of electrons in atoms also shape the formation of stars and galaxies. The quantum fluctuations that give rise to the uncertainty principle also gave rise to the cosmic structures that house billions of worlds. We live in a quantum universe, one where particles dance in superposition, where distant objects share instantaneous connections, and where the act of observation shapes reality itself. As we stand on the threshold of a new quantum age, with quantum computers, quantum communication, and quantum sensors beginning to transform our world, we are reminded that the most profound scientific revolution of the past century continues to unfold. The quantum world challenges us to expand our imagination, to embrace mystery and uncertainty as fundamental features of reality, and to recognize that the universe is far more remarkable than we ever dared to dream. From the smallest particles to the largest structures, from the briefest moments to the vast expanses of cosmic time, we are all participants in the grand quantum symphony that is our universe. In understanding quantum mechanics, we don't just learn about physics, we discover new ways of thinking about existence, knowledge, and our place in the cosmos. The quantum world reminds us that reality is not just stranger than we imagine, but stranger than we can imagine, and that there are always new frontiers of knowledge waiting to be explored. The quantum realm exists at the intersection of the incredibly small and the impossibly strange. It's a domain where the familiar rules of classical physics, the laws that govern our everyday experience, break down completely, replaced by principles so bizarre that they challenge our most basic intuitions about how the world works. To understand just how strange the quantum world is, consider this. In our everyday experience, objects have definite properties. A ball is either moving or stationary. It's either red or blue. It's either here or there. But in the quantum realm, particles can exist in what physicists call superposition, simultaneously possessing contradictory properties until the moment they're observed. It's as if that ball could be both moving and stationary, both red and blue, both here and there, all at the same time. This isn't simply a limitation of our measurement tools or a gap in our knowledge. According to quantum mechanics, these particles genuinely don't have definite properties until they're measured. The quantum world is fundamentally probabilistic rather than deterministic, built on possibilities rather than certainty. The discovery of quantum mechanics in the early 20th century represented one of the most revolutionary shifts in human understanding, since Copernicus revealed that Earth orbits the Sun. Scientists like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger didn't just discover new facts about nature, they uncovered an entirely different way that reality operates at its most fundamental level. One of the most profound mysteries of the quantum realm is wave-particle duality, the discovery that light and matter exhibit both wave-like and particle-like properties, depending on how we observe them. This revelation shattered the classical notion that everything must be either a wave or a particle, revealing instead that reality at the quantum level is far more fluid and context-dependent than we ever imagined. The story of wave-particle duality begins with light. For centuries, scientists debated whether light was a wave or a stream of particles. In the early 1800s, Thomas Young's famous double-slit experiment seemed to settle the question definitively in favor of wave. When light passes through two parallel slits, it creates an interference pattern on a screen behind the slits, alternating bands of brightness and darkness that can only be explained if light behaves as a wave. But in 1905, Albert Einstein complicated this picture when he explained the photoelectric effect by proposing that light consists of discrete packets of energy called photons. This particle-like behavior of light earned Einstein the Nobel Prize and helped establish the foundation of quantum theory. The plot thickened even further when scientists discovered that not only does light exhibit both wave and particle properties, but so does matter itself. In 1924, Louis de Broglie proposed that electrons, traditionally thought of as particles, also have wave-like properties. This was soon confirmed experimentally when scientists demonstrated that electrons can create interference patterns, just like light waves. The implications of wave-particle duality extend far beyond academic curiosity. This principle underlies many modern technologies, from electron microscopes that use the wave properties of electrons, to see incredibly small structures, to solar panels that rely on the particle properties of light to generate electricity. The dual nature of matter and energy reveals that the quantum world operates according to a logic that transcends our classical categories of thought. Perhaps no principle in quantum mechanics is more famous or more misunderstood than the Heisenberg uncertainty principle, formulated by Werner Heisenberg. This principle states that there are fundamental limitations to how precisely we can simultaneously know certain pairs of properties of a quantum system, such as a particle's position and momentum. The uncertainty principle is often misinterpreted as simply a limitation of our measurement tools, the idea that if we had better instruments, we could measure both position and momentum with perfect precision. But Heisenberg's insight goes much deeper than this. The uncertainty principle reveals that the universe itself has built-in limits to the precision of information it can contain. At the quantum level, the very act of measurement disturbs the system being measured. To determine a particle's position precisely, we must interact with it using photons, but this interaction necessarily changes the particle's momentum. Conversely, to measure momentum precisely, we must use techniques that inherently blur our knowledge of position. This isn't a technical limitation that might be overcome with better technology. It's a fundamental feature of reality itself. The mathematical expression of the uncertainty principle shows that the product of the uncertainties in position and momentum must always be greater than or equal to a specific value related to Planck's constant. This means that as our knowledge of one property becomes more precise, our knowledge of the complementary property must become less precise. The universe maintains a kind of cosmic balance, preventing us from achieving perfect knowledge of any quantum system. The uncertainty principle has profound implications that extend far beyond physics. It suggests that the universe is fundamentally indeterministic at its most basic level, challenging philosophical notions of causality and predictability. It also plays a crucial role in preventing atoms from collapsing. The uncertainty in electron positions and momenta provides the quantum mechanical pressure that keeps electrons from spiraling into atomic nuclei. Superposition stands as perhaps the most mind-bending concept in all of quantum mechanics. It's the principle that quantum systems can exist in combinations of all possible states simultaneously until they're observed or measured. This isn't merely a theoretical abstraction. It's a fundamental feature of quantum reality that has been confirmed through countless experiments and forms the basis for emerging technologies like quantum computing. To understand superposition, imagine flipping a coin. In classical physics, once the coin is in the air, it's either heads or tails. We just don't know which until we observe it. But a quantum coin would genuinely be both heads and tails simultaneously until the moment of observation. The quantum system exists in what physicists call a superposition state, a mathematical combination of all possible outcomes. The most famous illustration of superposition's strange implications is Schrödinger's cat, a thought experiment proposed by Austrian physicist Erwin Schrödinger. In this scenario, a cat is placed in a sealed box with a quantum system that has a 50% chance of triggering a mechanism that would kill the cat. According to quantum mechanics, until someone opens the box and observes the system, the quantum trigger exists in a superposition of both triggered and not triggered states, which would seem to imply that the cat is simultaneously dead. Schrödinger proposed this thought experiment not to suggest that macroscopic cats actually exist in superposition, but to highlight what he saw as the absurd implications of applying quantum mechanics to everyday objects. The paradox raises profound questions about where the quantum world ends and the classical world begins, a boundary that physicists are still working to understand. Real quantum superposition has been demonstrated with individual particles, atoms, and even small molecules. In these experiments, particles genuinely do exist in multiple states simultaneously. For example, an electron can be in a superposition of spinning clockwise and counterclockwise at the same time, or a photon can travel through multiple paths simultaneously in an interferometer. The practical applications of superposition are revolutionary. Quantum computers harness superposition to process vast amounts of information simultaneously. While a classical computer bit can be either 0 or 1, a quantum bit, qubit, can be in a superposition of both 0 and 1, allowing quantum computers to explore multiple computational paths in parallel. This quantum parallelism promises to solve certain types of problems exponentially faster than any classical computer could. Quantum entanglement. The universe's mysterious connections. If superposition challenges our understanding of individual quantum systems, then quantum entanglement shatters our notions of separateness and locality. Entanglement occurs when two or more particles become correlated in such a way that the quantum state of each particle cannot be described independently. The particles form a single quantum system, and measuring one particle instantly determines the state of its entangled partners, regardless of the distance separating them. The phenomenon of entanglement emerged from theoretical work by Einstein, Boris Podolsky, and Nathan Rosen. In what became known as the EPR paradox, they argued that quantum mechanics must be incomplete because it seemed to allow for instantaneous influences between distant particles, violating the principle that nothing can travel faster than light. Einstein famously dismissed entanglement as spooky action at a distance, believing that there must be hidden variables that predetermined the outcomes of quantum measurements. For decades, the debate over entanglement remained largely philosophical, but in 1964, physicist John Bell developed a theorem that provided a way to test whether the correlations predicted by quantum mechanics could be explained by local hidden variables. Bell's theorem showed that if quantum mechanics was correct, certain measurements on entangled particles would exhibit correlations stronger than any local theory could explain. Starting in the 1970s and continuing through today, experiments have consistently confirmed the predictions of quantum mechanics and ruled out local hidden variable theory. The most famous of these were conducted by Alain Aspect in the early 1980s. Though many subsequent experiments have closed additional loopholes and confirmed entanglement with ever greater precision, the implications of entanglement are staggering. When particles become entangled, they lose their individual identities and become part of a single unified quantum system. Distance becomes irrelevant. Entangled particles separated by meters, kilometers, or even light years remain connected in a fundamental way. Measuring one particle's spin as up instantly determines that its entangled partner will be measured as down, regardless of the spatial separation between them. This doesn't mean that information travels faster than light between entangled particles. The correlations are perfect, but they're also random. You can't use entanglement to send messages or information. What entanglement reveals is that the universe is non-local at its fundamental level. Reality isn't made up of separate, independent objects, but rather of interconnected systems whose properties are defined by their relationships rather than their individual characteristics. The combination of superposition and entanglement creates possibilities that seem to border on the magical. Quantum systems can exist in multiple states simultaneously and can be correlated across vast distances in ways that classical physics cannot explain. These phenomena are not just curiosities, they're being harnessed for practical applications that promise to revolutionize technology and our understanding of information itself. Quantum computing represents perhaps the most ambitious attempt to harness these quantum properties. By using qubits that can exist in superposition and can be entangled with each other, quantum computers can perform certain calculations exponentially faster than classical computers. While still in their early stages, quantum computers have already achieved quantum supremacy for specific tasks. solving problems that would be impossible for even the most powerful classical supercomputers. Quantum cryptography uses the principles of quantum mechanics to create unbreakable codes. Any attempt to intercept a quantum encrypted message necessarily disturbs the quantum states involved, alerting the communicating parties to the presence of an eavesdropper. Quantum key distribution systems are already being deployed for ultra-secure communications. Quantum sensors exploit the sensitivity of quantum systems to their environment to make incredibly precise measurements. Quantum magnetometers can detect magnetic fields millions of times weaker than Earth's magnetic field, while quantum clocks can keep time with unprecedented accuracy. These technologies have applications in navigation, medical imaging, fundamental physics research, and the search for dark matter. The theoretical implications of superposition and entanglement extend even further. Some interpretations of quantum mechanics suggest that superposition reflects the existence of parallel universes, alternate realities, where different quantum outcomes occur. In this many worlds interpretation, every quantum measurement creates a branching of reality, with all possible outcomes occurring in parallel universes. Among the various interpretations of quantum mechanics, none captures the imagination quite like the many worlds interpretation. First proposed by Hugh Everett III, this interpretation takes the mathematics of quantum mechanics to its logical extreme, suggesting that all possible outcomes of quantum events actually occur, but in separate parallel universes. According to the many worlds interpretation, when a quantum system is in superposition and then measured, the universe doesn't choose a single outcome. Instead, the universe splits into multiple branches, with each possible outcome occurring in a different branch. From the perspective of any observer in a particular branch, it appears that only one outcome occurred, but in reality, all outcomes happen, just in different parallel worlds. Consider the classic example of Schrödinger's cat. In the many worlds interpretation, when the box is opened, the universe splits into two branches, one where the cat is alive and one where the cat is dead. Both outcomes are equally real, but observers in each branch can only experience their particular reality. The cat is simultaneously dead in one universe and alive in another, with both realities being equally valid from the perspective of the quantum multiverse. The implications of this interpretation are staggering. Every quantum event, and there are countless quantum events occurring every instant throughout the universe, potentially creates new branches of reality. This would mean that there are an infinite number of parallel universes, containing every possible variation of history, every decision not made, every possibility not realized in our particular branch of reality. In some parallel universe, you might have chosen a different career, moved to a different city, or made different life decisions. In others, historical events might have unfolded differently. Perhaps the dinosaurs never went extinct, or humans never evolved, or entirely different forms of life emerged. The many worlds interpretation suggests that all of these possibilities are not just imaginary scenarios, but actual realities existing in parallel branches of the quantum multiverse. While the many worlds interpretation provides an elegant solution to some of the philosophical problems of quantum mechanics, eliminating the need for wave function collapse and maintaining the deterministic evolution of the universal wave function, it comes with its own conceptual challenges. If all possible outcomes occur, what makes our particular branch of reality special? How do we account for the apparent randomness of quantum measurements if all outcomes actually happen? One of the deepest mysteries in quantum mechanics is the measurement problem, the question of how and when quantum superpositions collapse into definite classical outcomes. This problem lies at the heart of our understanding of the relationship between the quantum world and the classical world we experience. In the mathematical formalism of quantum mechanics, systems evolve according to the Schrödinger equation, which preserves superposition states indefinitely. A quantum system left undisturbed will remain in superposition forever. But when we make a measurement, something dramatic happens. The superposition appears to collapse into a single definite outcome. The measurement problem asks, What exactly constitutes a measurement? Is it the interaction with a measuring device, the registration of the result in a computer, the observation by a conscious human being? Where exactly does the quantum world of superposition and uncertainty give way to the classical world of definite properties and determined outcome? Different interpretations of quantum mechanics provide different answers to this question. The Copenhagen interpretation, historically the most widely accepted, suggests that the act of measurement causes the wave function to collapse, but it doesn't specify exactly what constitutes a measurement. The many worlds interpretation avoids the measurement problem entirely by suggesting that collapse never actually occurs. All outcomes happen in parallel branches of reality. Other interpretations propose different solutions. The objective collapse theories suggest that wave function collapse is a real physical process that occurs spontaneously when quantum systems reach a certain size or complexity. The de Broglie-Bohm interpretation maintains that particles always have definite properties, but these properties are hidden from us until measurement reveals them. The measurement problem isn't just a philosophical curiosity. It has practical implications for emerging quantum technology. Understanding the boundary between quantum and classical behavior is crucial for building quantum computers, maintaining quantum entanglement over long distances, and developing quantum sensors with unprecedented sensitivity. Perhaps no aspect of quantum mechanics has generated more debate and speculation than the potential role of consciousness in quantum measurement. Some interpretations of quantum mechanics seem to suggest that conscious observation plays a special role in determining physical outcomes, leading to profound questions about the relationship between mind and matter. The connection between consciousness and quantum mechanics emerged from early attempts to understand the measurement problem. In the 1920s, some physicists, including Werner Heisenberg and Eugene Wigner, suggested that consciousness might play a special role in wave function collapse. The idea was that physical systems remain in superposition until observed by a conscious being, at which point the act of conscious observation causes the wave function to collapse into a definite state. This interpretation, sometimes called the consciousness-based interpretation, suggests that consciousness is not just an emergent property of complex physical systems, but rather a fundamental feature of reality that plays an active role in determining physical outcome. In this view, the universe is not just stranger than we imagine, it's intimately connected to the minds that observe it. The consciousness-based interpretation leads to fascinating questions. If consciousness causes wave function collapse, what level of consciousness is required? Does it require human consciousness, or would an animal consciousness suffice? What about artificial intelligence? Could a sufficiently complex computer program collapse quantum wave functions through its observation? However, most physicists today reject the idea that consciousness plays a special role in quantum mechanics. Modern experiments have shown that wave function collapse can occur through interaction with any macroscopic system, whether or not consciousness is involved. Quantum decoherence, the process by which quantum systems lose their coherence through interaction with their environment, provides a more widely accepted explanation for the transition from quantum to classical behavior. Yet the questions raised by the consciousness interpretation continue to inspire research and speculation. Some researchers have proposed that quantum effects in the brain might be responsible for consciousness itself, suggesting that the mind operates according to quantum principles. Others have explored whether quantum mechanics might provide insights into the hard problem of consciousness, the question of how subjective experience arises from objective physical process. Beyond the strange phenomena of individual particles, quantum mechanics extends to quantum field theory, a framework that describes particles as excitations in underlying quantum fields that permeate all of space. This perspective reveals an even more profound picture of reality, where the entire universe is composed of quantum fields constantly fluctuating and interacting according to quantum principles. In quantum field theory, what we think of as empty space is actually filled with quantum fields that are never truly at rest. These fields undergo constant quantum fluctuations, creating and destroying virtual particles in a cosmic dance of creation and annihilation. These quantum vacuum fluctuations have real, measurable effects. They contribute to the energy of atoms, affect the behavior of light, and may even influence the expansion of the universe itself. The implications of quantum field theory extend to cosmology and our understanding of the universe's origin and evolution. During the first fraction of a second after the Big Bang, quantum fluctuations in the primordial fields may have been stretched to cosmic scales by a period of rapid expansion called inflation. These quantum fluctuations would have provided the seeds for all the large-scale structure we observe in the universe today: galaxies, galaxy clusters, and the cosmic web of matter that spans billions of light years. From this perspective, the quantum realm isn't separate from the cosmic realm. It's the foundation upon which the entire universe is built. The galaxies scattered across the cosmos, the stars that light up the night sky, and the planets that orbit them all trace their origins back to quantum fluctuations in the very early universe. We are not just made of star stuff. As Carl Sagan famously said, we are made of quantum stuff, connected to the fundamental quantum fields that underlie all of reality. Recent developments in theoretical physics have revealed another mind-bending aspect of quantum mechanics: the holographic principle. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like how a hologram encodes three-dimensional information on a two-dimensional surface. The holographic principle emerged from studies of black holes and their thermodynamic properties. Stephen Hawking and Jacob Bekenstein discovered that black holes have entropy, a measure of information content that is proportional to the area of their event horizon, rather than their volume. This surprising result suggested that the information content of any region of space might be determined by its boundary, rather than its interior. The implications of the holographic principle extend far beyond black holes. Some theories suggest that our entire three-dimensional reality might be a holographic projection of information encoded on a two-dimensional boundary. From this perspective, the quantum realm might be even more fundamental than we previously thought, not just the foundation of physical reality, but the very information from which reality is constructed. This information-theoretic view of quantum mechanics has profound implications for our understanding of space, time. It suggests that what we perceive as solid objects moving through three-dimensional space might actually be emergent phenomena arising from more fundamental information processing on the boundary of the universe. The quantum realm becomes not just the domain of small particles, but the computational substrate from which all of reality emerges. The influence of quantum mechanics extends far beyond the atomic realm, playing a crucial role in shaping the large-scale structure of the universe itself. The cosmic microwave background, the afterglow of the Big Bang that we can observe in all directions of the sky, bears the imprint of quantum fluctuations that occurred in the first fraction of a second after the universe. During the inflationary epoch, when the universe underwent a period of exponential expansion, tiny quantum fluctuations in the energy density of space were stretched to cosmic proportion. These quantum uncertainties, governed by the Heisenberg uncertainty principle, provided the seeds around which matter would eventually clump together to form galaxies, galaxy clusters, and the vast cosmic web of structure that spans the observable universe. The cosmic microwave background, measured with exquisite precision by satellites like WMAP and Planck, shows tiny temperature variations that correspond exactly to what we would expect from quantum fluctuations in the early universe. These observations provide compelling evidence that quantum mechanics operates not just in earthly laboratories, but on the grandest scales imaginable. The connection between quantum mechanics and cosmology reveals a profound unity in nature. The same principles that govern the behavior of electrons in atoms also determine the distribution of galaxies across billions of light years. The quantum realm and the cosmic realm are not separate domains, but different aspects of a single, interconnected reality. Stars themselves are quantum mechanical objects, powered by nuclear fusion reactions that depend entirely on quantum tunneling. In stellar cores, temperatures reach millions of degrees, but even at these extreme temperatures, atomic nuclei don't have enough kinetic energy to overcome their mutual electrical repulsion. Through classical physics alone, quantum tunneling allows nuclei to approach each other closely enough for the strong nuclear force to bind them together, despite not having sufficient classical energy to overcome the electrostatic barrier. This quantum-enabled fusion process powers stars and creates the heavy elements that make planets and life possible. The quantum nature of stellar processes means that the light we receive from stars, the elements in our bodies, and the energy that powers life on Earth all have quantum mechanical origin. We are intimately connected to the quantum realm, not just through the atoms that compose us, but through the stellar processes that created those atoms billions of years ago. Even in the vast emptiness of space, between galaxies, quantum effects play important role. The quantum vacuum, far from being truly empty, seethes with virtual particle pairs that briefly pop into existence before annihilating each other. These quantum fluctuations contribute to the overall energy density of space and may influence the expansion of the universe itself. Dark energy, the mysterious force that appears to be accelerating the expansion of the universe, might be related to the energy of quantum vacuum fluctuations. While the theoretical predictions for vacuum energy are far larger than what observations suggest for dark energy, the connection between quantum mechanics and cosmic acceleration remains an active area of research. The quantum realm also manifests in astrophysical phenomena like pulsars, rapidly rotating neutron stars that emit beams of radiation. These objects are so dense that quantum effects become important even on macroscopic scale. The matter in neutron stars exists in exotic quantum states that cannot be reproduced in earthly laboratories, making these cosmic objects natural laboratories for studying quantum mechanics under extreme conditions. To understand how quantum mechanics shapes our universe, we must begin at the most fundamental level, the atom. For over a century, our understanding of atomic structure has been revolutionized by quantum mechanics, revealing that atoms are not the solid, indivisible particles once imagined, but rather complex quantum systems, where electrons exist in probability clouds around nuclei. The story begins in 1913, when Niels Bohr proposed his revolutionary model of the hydrogen atom. Unlike earlier classical models that predicted electrons would spiral into the nucleus, Bohr's quantum model showed that electrons could only occupy specific energy levels or orbits. This quantization of energy levels explained why atoms are stable and why they emit light at specific wavelength when excited. But Bohr's model was just the beginning. The development of full quantum mechanics in the 1920s revealed an even more remarkable picture. Electrons don't orbit the nucleus like planets around the sun, as Bohr had suggested. Instead, they exist in three-dimensional probability distributions called orbitals, regions of space where the electron is likely to be found. These quantum orbitals have strange and beautiful shapes. The simplest, called s orbitals, are spherical clouds surrounding the nucleus. The p orbitals are dumbbell-shaped, while d orbitals have even more complex geometries with multiple lobes. These shapes are not arbitrary. They are direct consequences of the wave nature of electrons and the solutions to Schrödinger's equation for the hydrogen atom. The quantum nature of electrons in atoms explains fundamental properties of matter that classical physics could never address. Why do atoms have specific sizes? Because the uncertainty principle prevents electrons from being localized too precisely near the nucleus. Why don't electrons fall into the nucleus? Because the quantum mechanical zero-point energy provides a kind of quantum pressure that keeps them in their orbitals. The periodic table itself is a monument to quantum mechanics. The arrangement of elements reflects the quantum mechanical filling of electron orbitals, according to the Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state. This principle explains why atoms have the electron configurations they do, why chemical bonding occurs, and ultimately, why matter has the rich diversity of properties we observe. The formation of chemical bonds, the forces that hold atoms together to create molecules and materials, is entirely quantum mechanical in nature. When atoms approach each other, their electron clouds begin to overlap, and the electrons must be described by quantum wave functions that span multiple nuclei. In a covalent bond, electrons are shared between atoms, occupying molecular orbitals that extend over the entire molecule. These molecular orbitals are quantum mechanical combinations of the atomic orbitals from the constituent atoms. The shapes and energies of these molecular orbitals determine the geometry, stability, and properties of molecule. The oxygen atom has partially filled p orbitals that can overlap with the s orbitals of hydrogen atoms. The quantum mechanical mixing of these orbitals creates bonding molecular orbitals that hold the molecule together and give water its characteristic bent shape. This quantum mechanical structure is responsible for water's unique properties, its high boiling point, its ability to dissolve many substances, and its crucial role in biological systems. The quantum nature of chemical bonding extends to all materials around us. The strength of steel comes from the quantum mechanical bonding between iron atoms and carbon atoms in specific crystalline arrangement. The semiconducting properties of silicon that make modern electronics possible arise from the quantum mechanical band structure created when silicon atoms bond together in a crystal lattice. Even the colors we see are quantum mechanical phenomena. When light interacts with matter, it can promote electrons from lower energy molecular orbitals to higher energy ones. The energy difference between these orbitals determines the wavelength of light absorbed, and thus the color we observe. The deep red of roses, the blue of the sky, and the green of chlorophyll all arise from quantum mechanical transitions in molecular orbitals. As we scale up from individual atoms and molecules to bulk materials, quantum mechanics continues to play a crucial role. The properties of solids, whether they conduct electricity, how they respond to magnetic fields, why some are transparent while others are opaque, are all determined by the quantum mechanical behavior of electrons in crystalline structure. In metals, electrons occupy energy bands that are partially filled, allowing them to move freely and conduct electricity. In insulators, the energy bands are either completely filled or completely empty, with a large energy gap between them that prevents electrical conduction. Semiconductors have small energy gaps that can be overcome with thermal energy or by adding impurities, making them essential for electronic devices. The quantum mechanical nature of electrons in solids gives rise to remarkable phenomena. Superconductivity, where materials lose all electrical resistance below a certain temperature, occurs when electrons form quantum mechanical pairs called Cooper pairs that can flow through the material without any energy loss. This purely quantum effect has applications ranging from MRI machines to quantum computers. Quantum mechanics also explains magnetism in material. The magnetic properties of iron, nickel, and cobalt arise from the quantum mechanical spin of electrons and how these spins align in the crystal structure. Even more exotic magnetic phenomena, like the quantum Hall effect, reveal the deep quantum nature of electrons in two-dimensional systems. The quantum mechanical properties of atoms and molecules ultimately enable the chemistry of life. The DNA double helix is held together by hydrogen bonds, weak quantum mechanical interactions between molecules that are strong enough to maintain the structure of genetic material, but weak enough to allow the strands to separate during replication. Proteins fold into their functional three-dimensional shapes due to a complex interplay of quantum mechanical forces, hydrogen bonds, van der Waals interactions, and electrostatic attraction. The specific folding patterns determine protein function, and misfolded proteins can lead to diseases like Alzheimer's and Parkinson's. Photosynthesis, the process that converts sunlight into chemical energy and powers most life on Earth, is fundamentally quantum mechanical. When chlorophyll molecules absorb photons, electrons are excited to higher energy quantum states. These excited electrons then participate in a cascade of quantum mechanical energy transfer processes that ultimately store solar energy in chemical bonds. Recent research has revealed that biological systems may exploit quantum effects more directly than previously thought. Some studies suggest that quantum coherence, the ability of quantum systems to exist in superposition states, may play a role in the efficiency of photosynthesis. Birds may use quantum entanglement in their magnetic compass systems for navigation. Even the sense of smell might rely on quantum mechanical recognition of molecular vibration. The birth of stars represents one of the most dramatic examples of quantum mechanics operating on cosmic scales. When clouds of gas and dust in space begin to collapse under their own gravity, they heat up as gravitational potential energy is converted to kinetic energy. But even when temperatures reach millions of degrees in stellar cores, classical physics alone cannot explain how nuclear fusion begins. The problem is the Coulomb barrier, the electrical repulsion between positively charged atomic nuclei. For hydrogen nuclei, protons to fuse into helium, they must get close enough for the strong nuclear force to overcome electromagnetic repulsion. Classical calculations show that the thermal energy in stellar cores is far too low to allow protons to surmount this energy barrier. This is where quantum tunneling comes to the rescue. In quantum mechanics, particles have wave-like properties, and their wave functions can extend beyond classical barriers. Even though protons don't have enough energy to classically overcome the Coulomb barrier, there's a finite probability that they can quantum tunnel through it. This quantum mechanical effect makes nuclear fusion possible at the relatively low temperatures found in stellar core. Without quantum tunneling, stars could never ignite. The universe would be a cold, dark place filled with failed stellar remnants called brown dwarfs. Objects that never achieved the quantum-enabled fusion reactions necessary to become true stars. The fact that we see a universe filled with shining stars is direct evidence that quantum mechanics operates on cosmic scales. The specific nuclear reactions that power stars are all quantum mechanical processes. In the proton-proton chain that powers our Sun, hydrogen nuclei undergo a series of fusion reactions, each step governed by quantum mechanical selection rules and tunneling probability. The rate of these reactions depends on quantum mechanical cross-sections and the wave functions of the nuclear states involved. Once fusion begins, the evolution of stars continues to be governed by quantum mechanics. The balance between gravitational collapse and radiation pressure from fusion reactions determines a star's structure, lifetime, and ultimate fate. But the details of this evolution depend critically on quantum mechanical processes in stellar interior. As stars age and exhaust their hydrogen fuel, they begin fusing heavier elements through quantum mechanical processes. Helium fusion creates carbon and oxygen. Carbon fusion produces elements like neon and magnesium, and silicon burning creates iron and nickel. Each of these fusion processes requires quantum tunneling to overcome increasingly large Coulomb barriers. As nuclear charges increase, the quantum mechanical properties of atomic nuclei determine which fusion reactions are possible and at what rates they occur. The fact that carbon-12 has a specific quantum state that enhances the fusion of 3 helium nuclei, a process discovered by Fred Hoyle and now called the Hoyle state, is crucial for carbon production in stars. Without this quantum mechanical coincidence, carbon would be extremely rare, and carbon-based life would be impossible. Stellar death is also governed by quantum mechanics. When massive stars exhaust their nuclear fuel, quantum degeneracy pressure, a purely quantum mechanical effect arising from the Pauli exclusion principle, determines whether the stellar remnant becomes a white dwarf neutron star or black hole. White dwarfs are supported by electron degeneracy pressure. The Pauli exclusion principle prevents electrons from occupying the same quantum state, creating a pressure that can support the stellar remnant against gravitational collapse. The maximum mass of a white dwarf, the Chandrasekhar limit, is determined by the balance between gravitational attraction and quantum degeneracy pressure. For more massive stellar remnants, electron degeneracy pressure is insufficient, and the stellar core collapses further. Electrons and protons are squeezed together to form neutrons in a process mediated by the weak nuclear force, another quantum mechanical interaction. The resulting neutron star is supported by neutron degeneracy pressure, again arising from the Pauli exclusion principle applied to neutrons. Neutron stars represent the most extreme quantum mechanical objects in the known universe. These stellar remnants pack more mass than the Sun into a sphere only about 20 kilometers across, creating matter densities that exceed those found in atomic nuclei. Under these extreme conditions, quantum effects dominate even on macroscopic scales. The matter inside neutron stars exists in exotic quantum states that cannot be reproduced in terrestrial laboratories. At the surface, nuclei are arranged in crystalline structures, forming the strongest solid material known. Deeper inside, nuclei become increasingly neutron-rich due to the quantum mechanical process of electron capture. In the outer core, nuclei dissolve into a sea of neutrons, protons and electrons, a quantum fluid unlike anything found elsewhere in the universe. Even deeper, the quantum state of matter becomes more exotic. Theoretical models suggest that neutron star cores might contain quark matter, free quarks and gluons existing in quantum states that normally only occur inside individual protons and neutrons. Some models even predict the existence of strange quark matter, or color superconducting phases, where the quantum chromodynamics of the strong force creates entirely new states of matter. The magnetic fields of neutron stars, which can be trillions of times stronger than Earth's magnetic field, arise from quantum mechanical effects in the extreme matter of these objects. These fields accelerate charged particles to relativistic speeds, creating the lighthouse-like beams of radiation we observe as pulsars. Black holes represent the ultimate frontier, where quantum mechanics encounters Einstein's general relativity. While black holes are primarily gravitational phenomena, quantum mechanics plays a crucial role in our understanding of their properties and behavior. The formation of black holes involves quantum mechanical processes. When a massive star's core collapses beyond the neutron degeneracy pressure limit, no known quantum mechanical force can halt the gravitational collapse. The star forms an event horizon, a boundary beyond which nothing, not even light, can escape the gravitational pull. But quantum mechanics doesn't disappear at the event horizon. Stephen Hawking's groundbreaking work in the 1970s showed that quantum effects near black holes lead to a remarkable phenomenon: Hawking radiation. Quantum fluctuations in the vacuum near the event horizon can create particle-antiparticle pairs, with one particle falling into the black hole while the other escapes. This quantum mechanical process causes black holes to slowly evaporate by emitting radiation. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning that smaller black holes are hotter and evaporate faster. For stellar mass black holes, the evaporation time is much longer than the age of the universe. But primordial black holes, if they exist, could be evaporating through quantum processes right now, potentially detectable through their high-energy radiation signature. The information paradox, the question of what happens to information that falls into a black hole, represents one of the deepest puzzles in modern physics, sitting at the intersection of quantum mechanics and general relativity. Quantum mechanics requires that information be conserved, but general relativity suggests that information falling into a black hole is lost forever. Resolving this paradox may require a quantum theory of gravity that unifies these two fundamental frameworks. The formation and structure of galaxies themselves have quantum mechanical origins. In the early universe, tiny quantum fluctuations in the energy density of space were stretched to cosmic scales during a period of rapid expansion called inflation. These quantum fluctuations, governed by the Heisenberg uncertainty principle, provided the seeds around which matter would eventually clump together under gravitational attraction. The cosmic microwave background, the afterglow of the Big Bang that we can observe in all directions, shows the imprint of these primordial quantum fluctuations. The tiny temperature variations in this radiation correspond to regions of slightly higher and lower density that would eventually grow into galaxies, galaxy clusters, and the cosmic web of large-scale structure. Computer simulations of galaxy formation start with these quantum-seeded density fluctuations and follow their evolution under the influence of gravity, gas dynamics, and stellar feedback. The intricate spiral arms of galaxies, the distribution of dark matter halos, and the hierarchy of cosmic structure all trace their origins back to quantum mechanical uncertainties in the first fraction of a second after the Big Bang. Even the dynamics of galaxies today involve quantum mechanics. The interstellar medium, the gas and dust between stars, undergoes complex chemical processes governed by quantum mechanical selection rules. The formation of molecules like hydrogen and carbon monoxide in space requires quantum mechanical transitions between different energy levels. Star formation within galaxies is triggered by the gravitational collapse of gas clouds, but the detailed physics involves quantum mechanical processes. The cooling of gas clouds depends on quantum mechanical transitions in atoms and molecules that radiate away energy. The opacity of stellar nurseries to different wavelengths of light depends on the quantum mechanical absorption properties of dust, grains and gas molecules. To understand how quantum mechanics shaped our universe, we must journey back to its very beginning. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this epoch, quantum mechanics played a fundamental role in determining the structure and properties of everything that would follow. Inflation theory proposes that the early universe was dominated by a quantum field called the inflaton field. This field had the remarkable property that its energy density remained nearly constant, even as space expanded, driving the exponential growth of the universe. But like all quantum fields, the inflaton field was subject to quantum fluctuations, tiny, random variations in its energy density that arose from the fundamental uncertainty principle. During inflation, these microscopic quantum fluctuations were stretched to macroscopic and even cosmic scale. Regions where the inflaton field had slightly higher energy density became the seeds for future overdensities in matter distribution, while regions with slightly lower energy density became underdense. These quantum-generated variations in energy density were imprinted on the fabric of space-time itself. When inflation ended and the universe transitioned to a radiation-dominated era, these quantum fluctuations became fluctuations in the density of matter and radiation. Over time, gravity amplified these tiny variations, causing matter to clump together in regions of higher density while leaving vast voids in regions of lower density. The end result is the cosmic web of structure we observe today, a universe filled with galaxies, galaxy clusters, and enormous voids, all ultimately tracing their origins to quantum fluctuations in the first 10 fast. The remarkable success of this picture is confirmed by observations of the cosmic microwave background. The tiny temperature variations observed by satellites like WMAP and Planck match precisely the predictions of inflation theory with quantum fluctuation. The statistical properties of these fluctuations, their amplitude, their scale dependence, and their nearly Gaussian distribution, all bear the signature of their quantum mechanical origin. The quantum mechanical processes that govern nuclear reactions were crucial not only for stellar nucleosynthesis, but also for the creation of the lightest elements in the early universe. During the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, Big Bang nucleosynthesis created the primordial abundances of hydrogen, helium, and trace amounts of lithium and beryllium. The success of Big Bang nucleosynthesis in predicting the observed abundances of these light elements represents one of the great triumphs of modern cosmology. But this success depends critically on the quantum mechanical properties of nuclear reaction. The cross-sections for nuclear fusion reactions, the energy levels of nuclear states, and the decay rates of unstable nuclei all arise from quantum mechanics and determine which nuclear reactions can occur at different temperatures and density. The quantum mechanical nature of nuclear processes explains why Big Bang nucleosynthesis produced roughly 75% hydrogen and 25% helium by mass, with only trace amounts of heavier elements. The binding energies of different nuclei, determined by quantum chromodynamics and the strong nuclear force, dictate which nuclear reactions are energetically favorable. The absence of stable nuclei, with mass numbers 5 and 8, creates a beryllium barrier that prevents significant production of elements heavier than lithium during Big Bang nucleosynthesis. This quantum-determined composition of the early universe had profound consequences for the formation of the first stars and galaxies. The high abundance of hydrogen provided fuel for the first generation of stellar fusion reactions, while the helium abundance affected the opacity and cooling properties of primordial gas clouds. The trace amounts of lithium created during Big Bang nucleosynthesis can still be observed in the atmospheres of the oldest stars, providing a direct link to the quantum processes that occurred in the first minutes after the Big Bang. After the cosmic microwave background was emitted about 380,000 years after the Big Bang, the universe entered what cosmologists call the Dark Age, a period when no stars had yet formed, and the universe was filled only with neutral hydrogen and helium gas. The formation of the first stars marked the end of this Dark Age, and required a complex interplay of gravitational collapse, gas dynamics, and quantum mechanical processes. The first stars formed in the gravitational potential wells created by dark matter halos, which had grown from the quantum fluctuations seeded during inflation. As primordial gas fell into these halos, it began to heat up due to gravitational compression. But for star formation to proceed, the gas had to cool and condense further, and this cooling process was entirely dependent on quantum mechanical transitions in atoms and molecules. In the metal-free environment of the early universe, cooling was primarily accomplished through quantum mechanical transitions in hydrogen atoms and the small amounts of molecular hydrogen, H2, that could form through slow chemical process. The efficiency of these cooling mechanisms determined how massive the first stars would be and how they would evolve. The first stars were likely much more massive than typical stars today, partly because the limited cooling mechanisms in the primordial universe prevented the formation of smaller stellar fragments. These massive first stars burned through their nuclear fuel rapidly, living only a few million years before exploding as supernovae or collapsing into black holes. When these first stars died, they enriched the interstellar medium with heavy elements created through stellar nucleosynthesis, elements like carbon, oxygen, silicon, and iron that were forged in stellar cores through quantum mechanical fusion process. These heavy elements, or metals in astronomical terminology, dramatically changed the physics of subsequent star formation by providing new pathways for gas cooling through quantum mechanical transitions in atoms and molecules. The quantum fluctuations that seeded structure formation during inflation grew over billions of years into the galaxies we observe today. This process involved a complex interplay between dark matter, normal, baryonic matter, and the quantum mechanisms that govern star formation and stellar evolution within galaxies. Dark matter, which makes up about 85% of all matter in the universe, played a crucial role in galaxy formation by providing the gravitational scaffolding on which normal matter could accumulate. While dark matter itself may be composed of exotic particles that interact primarily through quantum mechanical weak interactions, its gravitational effects drove the formation of the large-scale structure of the universe. As normal matter fell into dark matter halos, it underwent shock, heating, and cooling processes that were governed by quantum mechanical transitions in atoms and molecules. The balance between heating and cooling determined how efficiently gas could condense into dense regions where stars could form. The quantum mechanical properties of different atomic and molecular species, their binding energies, transition probabilities, and reaction rates, all influenced the star formation process. The formation of molecules like hydrogen, H2, carbon monoxide, CO, and water, H2O, in interstellar space requires quantum mechanical processing. These molecules not only provide cooling mechanisms that enable star formation, but also serve as tracers that allow astronomers to study the physical conditions in star-forming regions. The rotational and vibrational energy levels of these molecules, determined by quantum mechanics, produce the spectral lines that astronomers observe with radio and infrared telescopes. Star formation within galaxies creates feedback processes that regulate further star formation and galaxy evolution. When massive stars explode as supernovae, they inject energy and heavy elements into the interstellar medium. The production of these heavy elements through stellar nucleosynthesis, a quantum mechanical process, gradually enriches galaxies with the materials necessary for planet formation, and ultimately life. The role of quantum mechanics in shaping the universe extends beyond astrophysics to the evolution of life itself. The elements essential for life, carbon, oxygen, nitrogen, phosphorus, and others, were created through quantum mechanical fusion processes in stellar cores and distributed throughout galaxies by stellar winds and supernova explosion. The formation of planets around stars depends on the availability of heavy elements, which condense into solid particles in protoplanetary disks. The quantum mechanical properties of different elements determine their condensation temperatures and chemical behaviors, influencing the types of planets that can form at different distances from their host star. On Earth, the quantum mechanical properties of atoms and molecules enabled the complex chemistry that gave rise to life. The ability of carbon to form 4 bonds, the polar nature of water molecules, and the stability of the DNA double helix all arise from quantum mechanical effects in atomic and molecular orbitals. Photosynthesis, which powers most life on Earth, is fundamentally a quantum mechanical process. When chlorophyll molecules absorb photons, electrons are excited to higher quantum energy levels, initiating a cascade of energy transfer processes that ultimately convert solar energy into chemical energy. Recent research suggests that quantum coherence effects may even play a role in the remarkable efficiency of photosynthetic energy transfer. The genetic code itself may have quantum mechanical origin. The specific pairing rules between DNA bases, adenine with thymine, guanine with cytosine, depend on the quantum mechanical properties of hydrogen bonds. Mutations, which drive evolution, can occur through quantum mechanical processes like proton tunneling in DNA base pairs. Even more speculatively, some researchers have proposed that quantum effects in biological systems might play roles in consciousness, enzymatic catalysis, and other life processes. While these ideas remain controversial, they highlight the deep connections between quantum mechanics and the phenomena of life. Looking toward the future, quantum mechanics will continue to shape the evolution of the universe. The accelerating expansion of the universe, driven by dark energy, may itself be related to quantum mechanical effects in the vacuum of space. Some theories propose that dark energy arises from the quantum mechanical zero-point energy of fields, though reconciling theoretical predictions with observations remains a major challenge. As the universe continues to expand and cool, quantum mechanical processes will determine its ultimate fate. The evaporation of black holes through Hawking radiation, the decay of protons, if it occurs, and the eventual heat death of the universe all involve quantum mechanical processes operating over cosmological timescales. In the far future, quantum fluctuations may even allow for the spontaneous creation of new universes through quantum tunneling processes. Some theories suggest that our own universe might be part of an eternal multiverse, where quantum mechanics drives the continuous creation of new cosmic domains with different physical properties. At the heart of this transformation lies quantum computing, a technology so fundamentally different from classical computing that it represents not just an upgrade, but an entirely new paradigm for processing information. While classical computers process information using bits that exist in definite states of either 0 or 1, quantum computers harness the bizarre properties of quantum mechanics to create quantum bits, or qubit, that can exist in multiple states simultaneously through a phenomenon known as superposition. Imagine a coin spinning in the air. While it spins, it's neither heads nor tails, but both at the same time. This is analogous to how qubits behave, existing in what physicists call a superposition of states. But quantum computing doesn't stop there. Through quantum entanglement, qubits can be mysteriously connected across vast distances, creating correlations that Einstein famously called spooky action at a distance. These quantum properties allow quantum computers to explore multiple solution paths simultaneously, potentially solving certain types of problems exponentially faster than even the most powerful classical supercomputer. We're not talking about minor improvements. We're discussing computational advantages that could compress centuries of classical computing time into mere hours or days. The implications for drug discovery are particularly profound. Traditional pharmaceutical development is a painstakingly slow process, often taking decades and billions of dollars to bring a single drug to market. Much of this time is spent on molecular modeling, trying to understand how potential drug compounds will interact with target proteins in the human body. These molecular interactions involve quantum mechanical processes that are extraordinarily difficult for classical computers to simulate accurately. Quantum computers, however, are naturally suited to simulating quantum systems. They could revolutionize our ability to model complex molecular interactions, predict drug effectiveness, and identify harmful side effects before expensive clinical trials begin. This quantum advantage could accelerate the development of treatments for diseases like Alzheimer's, cancer, and rare genetic disorders, potentially saving millions of lives and trillions of dollars in healthcare costs. But the revolutionary potential of quantum computing extends far beyond medicine. In the realm of artificial intelligence, quantum algorithms could exponentially accelerate machine learning processing. Current AI systems require enormous amounts of data and computational power to recognize patterns and make decisions. Quantum machine learning algorithms could potentially identify patterns in data that are completely invisible to classical algorithms, leading to breakthroughs in everything from climate modeling to financial prediction. Consider the challenge of optimizing complex systems, from managing traffic flow in smart cities to coordinating supply chains across global networks. These optimization problems often involve so many variables that classical computers can only find approximate solutions. Quantum computers could potentially find truly optimal solutions to these problems, leading to more efficient cities, reduced waste, and improved quality of life for billions of people. As we explore the future applications of quantum mechanics, we encounter another revolutionary development: quantum communication. This technology promises to address one of the most pressing challenges of our digital age: cybersecurity. In our interconnected world, the security of our communications infrastructure is paramount. From banking transactions to government communications, from personal messages to corporate secrets, the confidentiality and integrity of our digital communications are essential to the functioning of modern society. Traditional encryption methods rely on mathematical problems that are difficult for classical computers to solve. However, the advent of quantum computers poses a significant threat to these conventional security systems. A sufficiently powerful quantum computer could break many of the encryption algorithms that currently protect our digital communications, potentially exposing sensitive information to malicious actors. But quantum mechanics doesn't just present a threat to cybersecurity, it also offers an elegant solution. Quantum communication leverages the fundamental principles of quantum mechanics to create communication systems that are theoretically unbreakable. This security doesn't rely on the computational difficulty of mathematical problems, but on the laws of physics themselves. The key insight comes from a fundamental principle of quantum mechanics: the act of observing a quantum system inevitably disturbs it. In quantum communication, information is encoded in quantum states, for example the polarization of photons. Any attempt by an eavesdropper to intercept and read these quantum encoded messages would necessarily disturb the quantum states, alerting the legitimate communicators to the presence of the eavesdropper. This phenomenon enables the development of quantum key distribution systems that can detect any attempt at interception with certainty. When two parties want to communicate securely, they can use quantum mechanics to establish a shared secret key that they know with absolute confidence has not been compromised. This quantum secured key can then be used with conventional encryption methods to ensure perfectly secure communication. The implications of quantum communication extend far beyond individual privacy. National security agencies are investing heavily in quantum communication networks to protect classified information. Financial institutions are exploring quantum-secured systems to protect trillions of dollars in transactions. Healthcare organizations could use quantum communication to securely share sensitive patient data while maintaining privacy. We're already seeing the early deployment of quantum communication networks. Countries like China have constructed quantum communication satellites and ground-based quantum networks spanning hundreds of kilometers. As this technology matures, we can envision a global quantum internet that provides unprecedented security for digital communications. But quantum communication promises more than just secure. Quantum networks could enable new forms of distributed quantum computing, where quantum computers in different locations are connected through quantum channels, creating computational networks of unprecedented power. These quantum networks could also enable new scientific discoveries by allowing researchers to share quantum information and coordinate quantum experiments across vast distances. Perhaps the most intriguing and controversial frontier in quantum mechanics lies in its potential connection to consciousness itself. For centuries, philosophers and scientists have grappled with the hard problem of consciousness. How does the 3-pound mass of neural tissue we call the brain give rise to subjective experience, to the rich inner world of thoughts, feelings, and sensations that define our existence? Traditional approaches to understanding consciousness have focused on classical physics and neuroscience, viewing the brain as a complex biological computer processing information through electrochemical signals between neurons. While this approach has yielded valuable insights into brain function, it has struggled to explain the subjective, qualitative nature of conscious experience, what philosophers call qualia. Some researchers have proposed that quantum mechanics might hold the key to understanding consciousness. This quantum theory of mind suggests that consciousness might emerge from quantum processes occurring within the brain's neural network. The idea is that the brain might be harnessing quantum effects like superposition and entanglement to process information in ways that classical physics cannot explain. One of the most prominent quantum theories of consciousness was proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum computations occurring within microtubules, protein structures found inside neurons. According to their theory, these microtubules can maintain quantum coherence despite the warm, noisy environment of the brain, enabling quantum processes that give rise to conscious experience. The implications of a quantum theory of consciousness would be profound. If consciousness truly involves quantum processes, it might explain some of the mysterious aspects of human cognition, our ability to make intuitive leaps, to process vast amounts of information seemingly instantaneously, and to experience the unifying, coherent nature of conscious awareness, despite the brain's distributed processing. A quantum understanding of consciousness might also have practical application. It could inform the development of more sophisticated artificial intelligence systems that truly understand and experience the world, rather than simply processing information. It might guide new approaches to treating mental illness and neurological disorders by targeting quantum processes in the brain. However, the quantum theory of consciousness remains highly controversial within the scientific community. Many neuroscientists argue that the brain is too warm and noisy to maintain the delicate quantum states required for quantum computation. They contend that classical physics and neuroscience are sufficient to explain consciousness without invoking quantum mechanics. The debate continues, but recent research has provided some intriguing evidence that quantum effects might indeed play a role in biological systems. Scientists have discovered quantum coherence in photosynthesis, where plants appear to use quantum superposition to efficiently transfer energy from sunlight to chemical energy. Similar quantum effects have been observed in bird navigation, enzyme function, and even potentially in the neural activity of fruit flies. As we look toward the future, we can envision a world where these different applications of quantum mechanics converge to create unprecedented technological capability. Quantum computers could be networked through quantum communication systems to create a global quantum computational infrastructure. This quantum internet could enable new forms of scientific collaboration, allowing researchers around the world to share quantum resources and conduct coordinated experiments. The integration of quantum computing and quantum communication could also enable new approaches to artificial intelligence. Quantum AI systems connected through quantum networks could potentially exhibit forms of distributed cognition that transcend the capabilities of individual classical computers. If consciousness does indeed involve quantum processes, these quantum AI networks might even develop forms of artificial consciousness. The pharmaceutical industry could leverage this quantum infrastructure to create unprecedented drug discovery capability. Quantum computers could simulate molecular interactions with perfect accuracy, while quantum communication could securely share sensitive research data between institutions. Quantum sensors could detect biological processes at the molecular level, providing new insights into health and disease. The path to this quantum future is not without challenges. Current quantum computers are still in their infancy, requiring extremely low temperatures and careful isolation from environmental interference. The quantum states that enable quantum computation are fragile and easily disrupted by heat, vibration, and electromagnetic interference. However, rapid progress is being made in developing more robust quantum systems. Researchers are exploring new types of qubits that are less sensitive to environmental noise, developing better error correction techniques, and creating more efficient quantum algorithms. Major technology companies and governments are investing billions of dollars in quantum research and development. The development of quantum communication networks faces similar challenges. Current quantum communication systems are limited in range and require specialized equipment. But as the technology matures, we can expect quantum communication to become more practical and widespread. The exploration of quantum consciousness remains in its early stages, with much fundamental research still needed to understand how quantum effects might contribute to conscious experience. This research could lead to revolutionary insights into the nature of mind and consciousness, with profound implications for neuroscience, psychology, and philosophy. You're holding a coin in your hand. You flip it into the air, and as it spins, you might think it's either heads or tails. You just don't know which until it lands. But what if I told you that in the quantum world, that spinning coin could literally be both heads and tails at the same time? What if the very act of looking at it determines its fate? Welcome to the quantum world, a realm so strange, so counterintuitive, that it challenges everything we thought we knew about reality itself. This is not science fiction. This is not philosophy. This is the quantum world that underlies every atom in your body, every star in the sky, and every fundamental process that makes our universe tick. Today, we embark on a journey of discovery through the most fascinating and mind-bending frontier of modern science, quantum mechanics. Quantum mechanics is perhaps the only field of science where the more you learn, the more mysterious it becomes. It's a world where particles can be in multiple places simultaneously, where two particles can be instantly connected across vast cosmic distances, and where the simple act of observation fundamentally changes reality itself. Consider the phenomenon of quantum superposition, the ability of quantum particles to exist in multiple states at once. Imagine if you could walk through multiple doorways simultaneously, take every possible path through a maze at the same time, or be in New York and Tokyo in the same instant. This isn't metaphor. This is exactly what particles do at the quantum level. An electron doesn't orbit the nucleus of an atom like a planet around the sun. Instead, it exists as a cloud of probability, simultaneously occupying every possible orbit until the moment we try to observe. Then there's quantum entanglement, what Einstein called spooky action at a distance, because even he found it difficult to accept. When two particles become entangled, they remain mysteriously connected, regardless of the distance separating. Measure one particle, and you instantly know the state of its partner, even if it's on the other side of the universe. Information seems to travel faster than light, defying our classical understanding of space and time. Perhaps most mind-bending of all is the role of the observer in quantum mechanics. In our everyday world, we assume that reality exists independently of whether we're watching it or not. A tree falling in an empty forest makes a sound, whether anyone hears it or not. But in the quantum world, the act of observation literally brings reality into existence. Before measurement, a quantum particle exists in a ghostly superposition of all possible states. Only when we observe it does it collapse into a definite reality. This isn't just theoretical speculation. These quantum effects have been demonstrated in thousands of experiments over the past century. They're as real and fundamental as gravity or electromagnetism, yet they operate according to principles that seem to mock our everyday experience of the world. Despite over a century of research, quantum mechanics remains one of the greatest frontiers in human knowledge. We've barely scratched the surface of what's possible in the quantum realm. Every new discovery opens doors to questions we never knew existed, revealing layers of mystery that beckon us deeper into the quantum rabbit hole. Consider quantum field theory, which attempts to reconcile quantum mechanics with Einstein's relativity. This theory suggests that what we think of as empty space is actually a seething ocean of virtual particles, constantly popping into and out of existence. The vacuum of space isn't empty at all. It's full of potential, waiting to be actualized. We're still unraveling what this means for our understanding of the universe's fundamental structure. Then there's the quantum measurement problem, one of the deepest unsolved mysteries in physics. We know that quantum systems exist in superposition until measured, but we don't truly understand why or how measurement causes the collapse into definite states. Is consciousness required for this collapse? Does the universe split into multiple realities, as some interpretations suggest? Or is there a more fundamental process at work that we haven't yet discovered? The exploration of quantum gravity represents another frontier where groundbreaking discoveries await. How do quantum effects operate in the presence of extreme gravitational fields? What happens to quantum mechanics near black holes or in the first moments after the Big Bang? These questions could revolutionize our understanding of space, time, and the very origin of the universe. Recent discoveries continue to astonish research. Scientists have observed quantum effects in increasingly large and complex systems, from individual molecules to microscopic biological structures. The boundary between the quantum and classical worlds seems to be more fluid than we once imagined. We're discovering quantum coherence in photosynthesis, quantum effects in bird navigation, and potentially even quantum processes in neural microtubules. Each of these discoveries raises profound questions. If quantum effects operate in biological systems, what does this mean for our understanding of life itself? Could evolution have harnessed quantum mechanics to create more efficient biological processes? Might consciousness itself emerge from quantum processes in the brain? The potential for revolutionary discoveries in quantum mechanics is virtually limitless. We're developing new mathematical frameworks, discovering new quantum phenomena, and pushing the boundaries of what's possible with quantum technology. Every experiment brings the possibility of stumbling upon something that could transform our understanding of reality itself. You might think that quantum mechanics is purely an academic pursuit, relevant only to physicists working in sterile laboratories. Nothing could be further from the truth. Quantum mechanics is already woven into the fabric of our daily lives in ways that would astonish our ancestors, and its influence will only grow more profound in the coming decades. Every time you use a smartphone, laptop, or any electronic device, you're relying on quantum mechanics. The semiconductors that power these devices work because of quantum effects. The LEDs that light our homes and screens operate through quantum processes. The GPS system that guides us through unfamiliar cities requires quantum mechanical corrections to maintain accuracy. Lasers, which are used in everything from barcode scanners to surgical procedures, are fundamentally quantum devices. Modern medicine increasingly depends on quantum mechanics. MRI machines use quantum properties of atomic nuclei to peer inside our bodies without invasive surgery. Quantum effects in molecular bonds allow us to develop new drugs and understand how medications interact with our cells. Quantum sensors are being developed that could detect diseases at the molecular level, potentially identifying cancer cells years before they become life-threatening tumors. The quantum revolution in computing promises to transform every aspect of human civilization. Quantum computers could solve problems that are impossible for classical computers, from modeling climate change to optimizing global supply chains. They could accelerate the discovery of new materials, leading to more efficient solar panels, better batteries, and revolutionary advances in energy storage. Quantum cryptography is already being deployed to secure sensitive communication. Banks are experimenting with quantum-secured financial transactions. Governments are developing quantum communication networks for national security. In the future, quantum encryption could protect every digital communication, ensuring privacy in an increasingly connected world. But perhaps most importantly, understanding quantum mechanics is crucial for making informed decisions about our technological future. As quantum technologies become more prevalent, citizens need to understand their implications. Should we be concerned about quantum computers breaking current encryption methods? How should we regulate quantum artificial intelligence? What ethical considerations arise from quantum-enhanced surveillance capability? Learning about quantum mechanics does more than expand our scientific knowledge. It fundamentally changes how we perceive reality. It teaches us that the universe is far stranger and more wonderful than our everyday experience suggests. It challenges us to question our assumptions and remain open to possibilities that seem impossible. The quantum world teaches us about the power of uncertainty and probability. In classical physics, if we know the initial conditions precisely, we can predict the future with certainty. But quantum mechanics shows us that uncertainty is fundamental to reality. This isn't a limitation of our knowledge, it's a feature of the universe itself. Embracing this uncertainty can lead to more nuanced thinking about complex problems in all areas of life. Quantum mechanics also demonstrates the profound interconnectedness of all things. Through entanglement, particles separated by vast distances remain connected in ways that transcend our classical understanding of space and time. This quantum interconnectedness might serve as a metaphor for the deep connections that exist throughout our world. From ecological systems to global economies to human relations. The observer effect in quantum mechanics reminds us that we're not passive observers of reality, we're active participants in creating it. Our choices about what to measure and how to measure it fundamentally shape the reality we discover. This principle extends beyond physics to remind us that our perspectives and actions play crucial roles in shaping our world. As we stand at the threshold of the quantum age, we're invited to embrace a sense of wonder that has driven human discovery for millennia. The quantum world challenges us to think beyond the boundaries of our everyday experience, to imagine possibilities that seem to violate common sense, and to remain humble in the face of nature's profound mysteries. The journey of quantum discovery is far from over. In fact, we may be entering the most exciting phase yet, as quantum technologies transition from laboratory curiosities to practical applications that will transform human civilization. Quantum computers, quantum sensors, quantum communications, and quantum materials are moving from research laboratories into the real world. But beyond the practical applications, quantum mechanics continues to offer profound insights into the nature of reality itself. It challenges our most basic assumptions about space, time, matter, and information. It suggests that the universe is far more interconnected, uncertain, and observer-dependent than we ever imagined. The quantum world is not just the domain of physicists and engineers, it's the fundamental reality that underlies everything we know and love. From the atoms in our bodies, to the stars in distant galaxies, from the devices in our pockets, to the thoughts in our minds, quantum mechanics governs it all. As we continue this journey of discovery, we're not just learning about quantum mechanics, we're discovering new aspects of ourselves and our place in the cosmos. We're developing technologies that could solve humanity's greatest challenges and unlock possibilities we can barely imagine. The quantum world invites us to think bigger, dream bolder, and remain perpetually curious about the deepest mysteries of existence. It reminds us that reality is far stranger and more wonderful than we ever dared imagine, and that the greatest discoveries may still lie ahead. In embracing quantum mechanics, we embrace a future where the impossible becomes possible, where the boundaries between science and wonder dissolve, and where the journey of discovery leads us ever deeper into the magnificent mystery of existence. The quantum world awaits, and the adventure has only just begun.